This module will address the very basics of maps. What are they? What are they good for? What kinds are there? What information do they contain? And how do we use them? A map is a picture or any other representation of features in nature in the same relative positions as they existed at the time that the data for the map were collected. That's an important point. It is a manufactured, miniaturized version of reality, a picture of your world, one that can often, but not always, but often be carried with you. So, what is the function of a map? I can use a map to see what there is in the area covered by the map. I can see where things are in relation to each other. I can help to determine where I am and where I want to go or what I want to do. And with regard to that last point, I can help to plan how I want to go to get there. How far will I have to travel? What features or obstacles can I expect along the way? And how might I be able to change my route in order to avoid certain obstacles? In other words, a major function of a map is in planning your route. So, what kinds of maps are there? That depends a lot on the goal of the map maker. What did that person want to achieve? Let's take a look at some examples. The best types of maps for backcountry travel are topographic maps like the one shown here. They contain a lot of information that you would need to plan your route or to see what's there. They show hills and valleys, elevations, water bodies, watercourses, trails, roads, towns and cities that may be in the area, distances, even latitude and longitude for exact placement. Lots of information. The U.S. Geological Survey, or USGS, produces a lot of maps of this type that are really absolutely necessary for planning a backcountry adventure. Maps such as the park map shown here are designed to show features that the park manager believes that the public would be interested in seeing or finding. Things like concession stands, playgrounds, shelters, comfort stations, things of that nature. There's much less of an emphasis or no emphasis put on things like topography or distances because they're not the goal of the map maker. There is, in this map at least, a legend on the left that helps to identify the different trails that are available for walking and the identities of some of the different pictures or symbols used to identify features of interest. Maps such as road maps have really very limited goals. They show geographic boundaries, they show cities and major towns, and they show the highways and the roads linking those cities and towns. There's very little to no other information included because highway travel is the goal of this kind of a map. Classroom globes give a very high-level look at the entire world. The classic globe shows the continents and major islands with the boundaries of the countries that existed at the time that the globe was made. The globe doesn't have to contain country boundaries. It could show economic zones, it could show ecological zones, it could show temperature or rainfall, or any other variable in which the map maker was interested and turned out to be the goal of the globe. However, it is a map. Relief maps are actually two-dimensional renderings of a three-dimensional landscape. The advantage is that not only do they allow you to see the location of features, such as towns, relative to each other, but allow you to see the elevation of those features relative to each other. Obviously, the features wouldn't have to be towns. They could be anything like vegetation, watercourses, water bodies, but they give you an idea of what the land might look like if seen in 3 dimensions. Coming soon from science fiction and into the realm of reality will be true 3-dimensional holographic maps of volumes, water bodies such as our oceans, our atmosphere, or even outer space. These three-dimensional maps will allow us to see in 3 dimensions the relative positions of features of interest and will allow for more effective navigation and route planning in those volumes. We've seen a series of very different kinds of maps. So the question now comes, what kind of information do maps contain, or what kind of information should maps contain? And again, that's going to depend on the goal of the map maker. A really good map, however, like a topographic map produced by the U.S. Geological Survey, would contain the 7 Ds. Let's take a look at these. So here are the 7 Ds that you'll find on a U.S. Geological Survey topographic map. Descriptions. What's the name of the area? And what information might be on the borders, such as the names of adjoining maps, latitude and longitude. Dates. When were the data for the map collected, and when was the map updated if that's the case? Directions. Which way is north, and which north? Geographic? Magnetic? Details, given by map symbols and colors. Designations, the names of important features such as rivers, mountains, cities, towns, and villages. Distances, given by a bar scale or an indication of the map scale and by contour interval. And finally, declination, UGG. We're going to talk about that in more detail a little bit later. Let's take a look now at a USGS map, see how many of the 7 Ds you can identify in this quick tour. Okay, let's look at some of these features in more detail. So here are examples of the descriptions that can be found on a map. In the upper right-hand corner of that topographic map, we find the name, the Newfoundland Quadrangle. USGS maps are called quadrangles. So here we have the Newfoundland Quadrangle in New Jersey. You'll notice sort of in the northeast corner there it says Greenwood Lake. That's the name of the quadrangle to the northeast of Newfoundland. There's a quadrangle name in each of the 4 corners, at the top and the bottom, and on the left and the right side, so that if you were doing route planning and your route went off the Newfoundland quadrangle, you would know which quadrangle to get to continue your route planning. You can also see longitude and latitude there in the northeast corner of the map, and those designations are given at regular intervals across the top and bottom of the map and up and down the 2 sides of the map. Dates. Here we can see that the data were collected for the Newfoundland quadrangle originally in 1954. And then in 1971, there was a photo revision to update the map as of that year. Directions. On most topographic maps and all USGS topographic maps, the sides of the map run up and down, geographic or true north and south. In addition, in the lower right corner of the frame, you can see what is sometimes called a compass rose, and there is a line with a star on top indicating the direction of true or geographic north. Details. You remember the little pictures and icons that we saw on the park map that we looked at previously? Well, topographic maps have similar symbols or icons. We can see some of those below. Blue is always going to indicate water, a water body, a stream, or a river. Green is going to represent vegetation, and black is used to represent man-made objects or structures. Sometimes you will see a highway that is rendered in red with black borders, and that's to indicate that it's a major roadway. Finally, as an example, we want to show you contour intervals, which appear in the next slide. We continue details with this slide of contour lines. Contour lines, usually rendered in brown, connect points of equal elevation above sea level. The closer together the lines, the steeper the terrain represented. The farther apart the lines, the less steep the terrain, even down to flat. And you can see all three of those conditions in this slide here. When you get to the point where you can read contour lines, you will actually be able to see the three-dimensional surface of the land rendered on that two-dimensional map. As a way of reinforcing the identity of map symbols with our scouts, we use some color pencils and poster board to create a chart, or a map symbols reference tool, which we then bring to each of our troop meetings and set up on an easel and encourage the scouts to go over, look, and learn. It seemed to work relatively well with our scouts. Designations. Let's look at some examples of designations on a USGS topographic map. So here's the town of Newfoundland, after which the quadrangle was named, and you can see the gravel pit just to the north of Newfoundland. If we scan down here, we can find Charlotteburg and Green Pond Junction. Then if we spin over here to the west, here is Green Pond Mountain, Browns Pond. And there's Green Pond itself with the East Shore Road along its southeast side. There's the town of Green Pond. Here we can see the Timber Brook. And then down at the south end, we see Farney State Park and Split Rock Reservoir, which are right near what? Winnebago Scout Reservation. So you can see how designations work on a topographic map. Distances. At the bottom center of the Newfoundland quadrangle is information to help you calculate or find distances on the map. So the scale of 1 to 24,000 means 1 unit on the map equals 24,000 units on the ground. 1 inch on the map equals 24,000 inches, or 2,000 feet, or something over 1/3 of a mile on the ground. Below the scale is a series of bar scales that help you measure distance directly without having to do arithmetic. Now, the thing to remember with the scale and the bar scales is that they show you distance as the crow flies. Walking distance up and down over rough terrain may actually indicate more ground miles than as the crow flies miles. You need to take that into account. Finally, below the scales is an indicator that the contour interval is 20 feet. That means that the vertical distance between contour lines is 20 feet. Finally, declination, sometimes called variation. Declination is the difference in direction at map center between magnetic north and geographic or true north. And on this compass rose, we can see that geographic or true north is indicated by the star. Sometimes it will be indicated with a T or TN. Magnetic north, slightly to the left, is indicated here by MN, sometimes just indicated by M. And the declination, or difference in direction, is 11 degrees, and you can see that it is 11 degrees to the west. So declination here is 11 degrees west. Now down at the bottom, it says 1971 magnetic north declination at center of sheet. We're going to see in a moment why 1971, or the date at which declination was determined, is important. All right, why is declination important? If you're going to use a map and compass together, you have to be able to account for the difference between the two norths. This is important in navigation. Okay, but why might the date be important? The date is important because magnetic north is not fixed. It moves over time. Since the location of the magnetic North Pole was first identified in 1831, it has moved steadily northward, out of Canada and towards Siberia. Since 2000, the speed has increased from approximately 10 miles per year to approximately 40 miles per year, and in early 2020 it was confirmed to have crossed the anti-meridian, technically into the other half of the world. If you're not familiar with the term anti-meridian or prime meridian, you need to review the module on the basis for the basics of map and compass. So how significant is the changing location of magnetic north for us? Well, that depends on who us is. Fortunately, in the lower 48 states, it's not very significant unless you're a surveyor working over a large area where small differences in direction can have big implications for borders and boundaries. For some areas of the world, however, the change in declination can be significant. For example, let's look at the difference between Newfoundland, New Jersey versus Barrow, Alaska, the northernmost point in the United States. In 1971, declination in Newfoundland, New Jersey was estimated to be 11 degrees 31 minutes west. 50 years later, declination was estimated to be 12 degrees 35 minutes west, a difference of 1 degree, well within the margin of error for scout compasses and the kind of navigating we do in scouting. In Barrow, Alaska, however, that difference between 1971 and 2020 turned out to be 13 degrees. In case you're wondering, we also looked at the difference in declination over the same time period for Anchorage and Juneau, which are further south, and the difference in declination was much the same. Therefore, the use of a 1971 map in 2020 Alaska could lead to some significant inconvenience. If you want to do some investigating of changes in declination on your own, and you should if you're going to be doing a backcountry adventure, you really need to know what the current declination is in the area in which you'll be traveling, hiking, camping, or backpacking. In order to determine the change in declination or the current declination, go to the link indicated in blue and then follow the directions. When you follow the link, here's the page to which you'll be brought. Then look at the link toward the center in the red circle that says declination. Click on that link. It will take you to a page that will give you several different options for determining declination in whatever area you plan to be. One last thing about using your map. In order to use your map effectively, you first have to orient the map. That means you have to hold or place the map so that the features on the map are in the same relative position as in nature. Then you can determine where things are when looking from map to nature. You can do this without any other tool by finding observable, identifiable features out in nature and then turning or moving the map so that map features and natural features line up. Let's take a look at an easy example so that you can see what we mean. Suppose for a moment that you're in Cadia National Park in Maine. You've taken the shuttle bus out to the Jordan Pond House to have lunch, and having finished, you walk across the lawn to the edge of Jordan Pond. Across the pond in the distance, you see two small mountains, one slightly behind the other and a larger mountain to the right. Now you've heard that somewhere in this area is a place called Sargent Mountain, from the top of which you can see some really nice views. You'd like to get there, but you're not sure how to proceed from this point. What do I do? I'll get out my map. So I get out my map and I hold it in front of me. Something doesn't look right. When I look across the pond, I see a big mountain instead of two small mountains, and the two small mountains seem to be off to the left, and the Jordan Pond house by that little bus symbol seems to be off to the right instead of behind me. It doesn't look like this at all. What to do? Perhaps if I rotate the map, if I orient the map, I can get a better view. Let's try that. Okay, I've rotated my map now, and things look a little better. As I look up and I look at the map, there are the two small mountains, one slightly behind the other, in front of me across the pond, and there's a large mountain to the right of the two small mountains, and the little bus symbol at the Jordan Pond house is where it should be, behind me. I'll bet my map is now oriented correctly. So when I look up from my map, I can see that the features in nature and the features on the map are in the same relative positions. So my map is now oriented to the point where I can see where things are and how I might want to go to get there. I can see that Sargent Mountain is at the other end of Jordan Pond, and if I walk up the left side of the pond from where I am, I'll find a trail that will take me to the top of Sargent Mountain. This was a particularly easy example, and we chose it as such to make it simple to show you how orienting a map by features would work. Unfortunately, it will not always be this easy. There are going to be situations where there simply are no observable features. For instance, you're in a boat in the middle of the ocean. All you can see is water and sky. Or it may be that observable features are there, but you can't see them because they're obstructed. You're in the middle of a forest, surrounded by tall trees, and you can't see out from where you are. Instances like this is where you need another tool to help you orient the map and navigate, and that's where a compass comes in handy. And in the module called Putting It All Together, Combining Map and Compass, we'll show you how to use a compass to orient the map and help you in navigating your backcountry adventures. You now have the very basics about maps. From here, you should be able to go to other sources, like your Scout Handbook, and find more information, tips, and tricks. When maps are used together with a compass, which is the subject of a different video module, you have powerful tools that will help you to navigate your field and backcountry adventures. We hope that you've enjoyed this video on maps and found it informative. We invite you to view the other videos in this series on using map and compass. Good luck in your adventures, Scouts and Scouters.